Thank you very much. To begin with, I would like to introduce myself. My name is Andrei Coman, and I am a student at the Tudor Vianu National High School of Computer Science. So I would like to begin with addressing my thanks to the Romanian Academy Center for Artificial Intelligence, and especially Academy member Dan Tufiș for offering me this opportunity of participating in an international project in collaboration with the Romanian Academy. I will present how we addressed the issues of the MARCELL project, which I will now introduce. MARCELL stands for Multilingual Resources for CEF-AT in the legal domain and is coordinated by the Research Institute for Linguistics of in the Hungarian Academy for Sciences. It involves 7 countries. As you can see, Bulgaria, Croatia, Hungary, Poland, Romania, Slovakia, and Slovenia. And it aims to provide automatic translations for the legal corpora of these countries. Its main objectives are processing these legal corpora, classifying them in the Eurovoc categories, and enriching them with Eurovoc and IATE terminology. It also aims to provide a comparable corpus of those 7 legislative databases. We process the Romanian legal corpus, which consists of 148,090 documents spread out along several periods, as you can see there, about 300 documents from 1881 to 1949, almost 4,000 documents from 1950 to 1989, to 21,000 documents from 1990 to 1999, and a little bit above 123,000 documents from 2000 to the present. This corpus consists of several types of documents, among which are governmental decisions, ministerial orders, decrees, and so on. As I mentioned earlier, this project consisted of several steps, the first of them being annotating and introducing the IATE terminology in the corpus. There are possible several approaches to this issue, and we decided to view it as a string matching problem, namely an approximately string matching problem. And therefore we considered several concepts, several ideas for this string matching problem, some of which I will present to you and which were actually rejected due to their significant downsides. And I will continue with the final algorithm for which we introduced a compression function and built it around the Aho-Corasick data structure. Our first approach was, well, to begin with, we had to introduce the definition of a match. How do we match one term in the database with one term in the corpus? And since the Levenshtein distance is one of the most common such measures for this discrepancy in terms, we chose to study if the Levenshtein distance is suitable for our problem. So, considering the Levenshtein distance, the most natural approach would be to continue with Levenshtein automata, which I'm sorry if some of you already know this, but Levenshtein automaton is a simple finite automaton which, for a given standard word, accepts only those words situated at a maximum given distance, Levenshtein distance, from the standard word. So we had to create such an automaton for each term in the database, then pass the corpus through this automata, and for the already existent multi-word terms, do a pattern matching. Some of the downsides are already obvious, as mentioned here. The first one would be that we cannot add any further constraints, we cannot easily add any further constraints to the Levenshtein distance criteria due to the structure of the automaton. So this makes it partially unsuitable for processing the Romanian language and any language in general, because languages have particularities and so on. And further, it is very demanding in terms of computational complexity. One approach would be to create, as I said, an automaton for each individual word, then pass the corpus through them, and then do pattern matching for them. The process of merging automata is highly demanding. To avoid this, we could create an automaton for each term. So we would have some automata for single word terms and some for multi-word terms. This would require us to pass through the corpus several times for each possible length of the term. And thus, since the corpus has approximately 33 gigabytes, would have been unsuitable. In order to surpass these disadvantages, we decided to think of Aho-Corasick, continuing with the Levenshtein distance, because Aho-Corasick offers a linear time processing. So instead of creating this automata, we could manually generate all the words situated at the respective Levenshtein distances from the standard words, insert them in an Aho-Corasick structure, and then pass the corpus through that respective structure. This allows us to add other constraints other than the Levenshtein distance, because the words are now manually generated. Manually meaning that we have to generate them however we want to, for example, through backtracking. This also has some disadvantages because of the number of actual terms which have to be introduced in the structure. The number of terms situated at a maximum Levenshtein distance from a standard is actually exponential in the length of the respective word. So since the corpus has terms which consist of up to several hundreds of characters, we could not actually generate all these matches, even though we could add other criteria for generating them. Therefore, we concluded that Levenshtein distance is indeed not suitable, because the algorithm which does not generate the words themselves creates the need for additional computational time by merging automata and passing through the corpus several times. And if we want to generate all the matches, even linear time processing, which follows the pre-processing, is not enough for this algorithm to be viable. So we decided to introduce the concept of a compression function. Therefore, we wanted to take advantage of the fact that we are actually processing a language, the Romanian language, which has some or many redundancies in its terms. Since we do not have any prior data for this Yate terminology, we only had to work with the actual structures of the words, with the letters and their order. So we wanted to create a compression function which would give us kind of a lemma for a given word. So if a word is passed through this compression function, it would give us a lemma, a pseudo-lemma, which would correspond to what we would get by getting other terms which represent other forms of the same word. For example, we initially we analyzed how the structures of these words vary as we modify their forms, and in most of the cases, the consonants remained unchanged, while the vowels changed constantly. So the first idea of a compression function would be to only keep the consonants out of the words. For example, for the term excepție de constituționalitate, we would get that mask, that pseudo-lemma. After solving some issues with this string matching, because obviously this was not enough, we decided to further keep spacing in our pseudo-lemmas, and then, based on the fact that some studies prove that our brains, when processing words, only need to have the first and the last letters in place, and the other letters may be scrambled, we decided that out of all the information, the first letter would be the most important for actually identifying a word. So we kept the first letter in addition to keeping the consonants and spacing. Any additional constraints for processing the words in the dictionary would be, for example, treating capitalization for abbreviations, because many abbreviations are only consisting of a few characters and tend to be confused with other Romanian words. For example, the term AU, which stands for the chemical element gold, would be commonly mismatched with the common particle au from Romanian, which obviously is not desirable. Based on this concept of a compression function, we designed the following algorithm. First, we would pass the iate terms, all the terms in the dictionary, through this compression function, and instead of inserting the terms themselves in the Aho-Corasick structure, we would insert the pseudolemmas. Then we would pass the actual corpus through the function and pass the corpus through the Aho-Corasick structure. It's also noteworthy that when using Aho-Corasick, we no longer need to do any additional processing for multi-word terms, since Aho-Corasick just takes the text character by character, no matter the starting position of the matches. This also had some downsides, although it gave extraordinary results. It behaved very well for long words, but for shorter words, it was clear that we were neglecting way too much information from the additional structure. So we decided to create a separation between the processing of those two categories. So for the terms of at least 5 consonants, we would use the previously described algorithm, namely passing the terms and the corpus through the compression function and using an Aho-Corasick structure. And for the other terms, the shorter terms, we would just insert the terms as they are in another Aho-Corasick structure, then pass the corpus through with its initial form through the same structure. Those matches obtained through those two algorithms would then be merged and introduced into the actual corpus. The results that we obtained were the following. We obtained a bit over 51 million matches, 29 million short terms and 22 million long terms, which stands for approximately 347 matches per document. We were also able to split the documents into the Eurovoc categories, the 21 already established categories, as you can see in this table, also on the screens. And this is a sample of how the documents looked. So on the first columns, we had the initial information. Then on the last column, the ID of the match. Then the iate index. Then the Eurovoc categories corresponding to each term. Any questions?
Thank you very much for the very nice presentation you had.
Thank you.
Please, Professor Christian.
Very interesting. We are doing some studies related to interpreting all documents, Romanian documents, starting from, perhaps you have been in the room yesterday evening, from Cyrillic, the transcription. I mean, originally they are in the Cyrillic language, alphabet. And the terms, the words are, of course, in many cases different than the modern form of them. And I would wonder if your techniques could not apply to this, because what we thought we could do is to kind of cluster flexible linguistic forms of the same lemma, and to first recognize these clusters and then to label them with a lemma, for instance, ideally with a lemma, but an entry from a dictionary, modern dictionary, would be perfect. Do you have an idea on this?
Well, I forgot to mention that this approach is based on the fact that we had a completely lemmatized corpus and a partially lemmatized dictionary. The Yate dictionary is lemmatized for the short words, sorry, consisting of only single word terms, and is not lemmatized for longer words. So as long as these conditions are met and we have a language and a suitable compression function for that language, this algorithm could still be applied and would obtain similar results. So considering that the terms themselves modify or the dictionary modifies, as long as we can find a suitable compression function, we could still use the same idea and the same concept.
Some other questions? Not yet, but there will be.
Thank you very much.
Thank you very much.